Our universe is absolutely massive. It's approximately 46.5 billion light-years in diameter. Scientists have attempted to map the universe using instruments designed to survey the night skies. These surveys are then compiled into accessible datasets, which people can use to visualize the cosmos in fascinating ways. These surveys cover a wide range of products. From Gaia star data to distant quasars, scientists have discovered countless objects in their search of the night sky. They allow us to take a look at fascinating visualizations of the profoundly interesting structure of our universe. Let's begin with nearby stars. Scientists use what is called parallax to deduce how far away something is, based on how the object moves relative to the changing position of an observer. Parallax becomes evident when you take the same picture, yet from slightly different positions. Let's take a couple of photos from outer space. We'll use these two photos. Now we'll take a look at where the star was positioned in the sky in each photo. Let's say that the star in the first photo was positioned at 30.01 degrees, and in the second photo it was positioned at 29.99 degrees. Now we know that the angle where the star appears to wobble in the sky is 0.02 degrees. Now we can visualize exactly what's going on here. These two photos, taken 6 months apart, were taken when Earth was on opposite sides of the Sun, making the star appear to be in different positions in the night sky. We can take the angle we measured, 0.02 degrees, and place it here. We can split a line down the middle, with each angle now being 0.01 degrees. Then, being vertical angles, we can find this angle to be 0.01 degrees. Since we know the average distance between the Earth and the Sun is 93 million miles, we have everything we need to find the distance between our star and the star we're looking at. Since we took these photos on opposite sides of the Sun, we have one side length and one angle in a right triangle. Using basic geometry, we can find the approximate distance between this star and our star by solving the equation for x. We find that our distance is equal to 500 billion miles. Most times, star parallax angles are measured in milliarc seconds, which are 1,000th of 1/60th of 1/60th of a degree. If we used a real example of Proxima Centauri, the closest star to our Sun, and we took the measured parallax angle of 770 milliarc seconds, we would just plug in the following equation, which gives us a distance of 24.9 trillion miles. And this is the true distance between Proxima Centauri and Earth. This allows us to accurately map billions of stars, being compiled in datasets such as Gaia DR3 by the European Space Agency, which is being visualized here in Space Engine Pro. This visualization features 30 million stars from the DR3 dataset, a small fraction of the billions of objects cataloged therein. Our instruments can only become so accurate, and galaxies are simply way too far for us to use parallax to accurately determine their distance. If we were to map some of the most distant galaxies in the observable universe, we would need to come up with something different. Fortunately, we have exactly that. This is the Sloan Digital Sky Survey, featuring millions of galaxies. This survey was created using galactic redshift, a phenomenon where light waves become longer because an object is moving away from us. We can then calculate the distance using Hubble's law, which says that the distance a galaxy is from Earth is proportional to the velocity at which the galaxy is moving away. And this is a direct result of the idea that the universe is expanding. But how exactly did we prove Hubble's law in the first place? Scientists noted a strong correlation between the redshift and distance of galaxies. To find the distance of these galaxies, scientists use objects with a known brightness. The inverse square law states that something's apparent brightness depreciates quadratically, meaning if we know how bright something actually is, and we know how bright it appears from the observer, then we can find the distance between the observer and the object itself. With this fundamental fact, scientists can use objects with a known brightness and calculate that object's distance from Earth. For example, Cepheid variable stars pulse at a rate strongly correlated with its brightness, meaning we can observe how fast those stars pulse, infer their brightness, and calculate their distance with the inverse square law. After that, we simply measure the redshift of the galaxy the star resides in, and do this a bunch of times with a bunch of different galaxies, and we would be able to observe a statistical pattern. The redshift of a galaxy is directly proportional to its distance. Using these observations, we can infer the distance of galaxies simply by measuring their redshift. And once a survey is able to measure the redshift of millions of galaxies, scientists can plot these galaxies in 3D space, allowing us to see the beautiful structure of our universe.